Good day, everybody. It's week 11 of our course, and it is time to review for exam 2. So looking at exam 2, some of the topics we'll need to know. We're going to need to know how to use the normal probability still. That was right at the end of exam 1. Then the normal probabilities and how they connect in with sampling distributions. Now remember, sampling distributions kind of connect in with our central limit theorem. And then sampling distributions lead directly into confidence intervals. Remember, in confidence intervals, you have point estimates, which is just that single number from the sample. You might just use the sample mean to estimate the population mean. That's a point estimate. Then use the interval estimate, which is the confidence intervals. Of course, that interval estimate deals with a margin of error that we will look at in just a little bit. And then finally, in the last week, we have had the basics of hypothesis testing. Okay, so let's take a look at some of the things we'll need to understand here for this test. We do need to understand probabilities and probability density curves. Probability density curve might look something like this. It's kind of like a bell curve, but maybe skewed a little bit. And remember, the area under the curve is always equal to 1. And let's put in some values here. I'm just going to do 1, 2, 3, 4, 5, 6, whatever. And I'm going to fill in that this section here has a probability of 0.19. This section over here, this tail, I'm going to give it a probability of 0.06. And this one will give it a 0.31. So now if I ask you what is the probability of being less than 3? Well, that means I've got to add up all these probabilities that are less than 3 here. I add all those up, what do I get? 0.56. I might ask what's the probability of being greater than 2? Well, here's 2 being greater than 2. I don't know all these probabilities over here, but I know the whole curve has to add up to 1. So I would take 1 and I would subtract these probabilities over here. 0.19 plus 0.06. That would work out to be 0.75. So dealing with those probabilities under the curve and knowing how to add them up and knowing the fact that the whole curve equals 1. So even though you're not given these probabilities over here, you know that they all have to add up to whatever makes that total equal 1. Okay, so then dealing with our confidence intervals. Some vocabulary we need to know. We need to know point estimate, as we mentioned. And we need to know margin of error. And how would we get that from the interval? Let's say we punched it in a calculator, and a calculator gives us an interval of 106, 128. The point estimate is always at the very center of the interval. So for the point estimate, we can just find the average of the endpoints. 106 plus 128 divided by 2. That gives us 117 would be our point estimate. margin of error. But once I have the point estimate, I could just take the point estimate and subtract one of those two numbers to get the difference. Or I can just find the range of the interval, 128 minus 106, and divide that by 2, which is going to give us 22 divided by 2 is 11 is our margin of error. So that would be plus or minus 11 would be the margin of error. So now let's say that we're told that this is a 90% confidence interval. What that means doesn't mean that 90% of all confidence intervals will contain that mean, or 90% will be within that range. No, what it means is we are 90% confident that the true population mean, is between 106 and 128. So what that's saying is, remember we talked about that whole distribution, the fact that if you have the mean of the population, the mean of the samples is going to be distributed around that population mean. And so what we're doing is we're finding a range that is wide enough that it would contain 90% of those sample means. But we're not starting with the population mean, we're starting with the sample mean. So 90% of the sample means would be close enough to that so that that range would include the population mean, but not always. So this statement is very careful. We're not saying that 90% of the time the mean will fall within this range. That's not true. We're saying we're 90% confident that this range contains the population mean because we went out far enough, and again, I'm going to blur the words a little bit. We went out far enough that 90% of those means would be close enough that that range would cover it. Now we're going to go over actually finding confidence intervals a little bit more in a bit. Just going over some of the vocabulary right now. For hypothesis testing, remember we have a null hypothesis, an alternative hypothesis. The null hypothesis is always the status quo, or whatever an accepted value is. And the null hypothesis is always stated as the population mean is equal to a number, whatever it is. In this textbook, it's always equal to. Other textbooks vary a little bit, but the null hypothesis will always be mu is equal to, or if it's a proportion, p is equal to. So it must be equal to, and it must be the population parameter that we're referring to, not a sample parameter. So it can't be x bar, it has to be mu. The alternative hypothesis then can be less than, greater than, or not equal to. But those can only appear in the alternative. We have our errors. A type 1 error when we are hypothesis testing. Type 1 error is when the null is true. So in reality, the null hypothesis here is true, but our test rejects it anyway. Another way of wording it is you reject a true null hypothesis. So even though it was true, the results of your test caused it to be rejected, which means you just happened to get a sample that was way out on one of the ends of that curve that had a mean or proportion that was way out on the tails of that bell curve, and it is possible. Now the probability, the probability of getting a type 1 error is always equal to our significance level. So if we are doing, and that's alpha, if alpha is 0.05, what that is saying is there is a 5% chance of getting a sample that will cause us to reject HO even when it's true. So what we're saying is, we're doing that curve around the population mean, and we're doing that 95%, or that 0.05 means we're forming a 95% confidence interval around that mean within our sampling mean, our sample means, but there's still that small chance that it could be on the outside. Now I formed this as a confidence interval, but it could be left-tailed or right-tailed. I did this as two-tailed. But still, there is that chance that even though that null hypothesis is true, that we have one of those outlying samples that puts us, gives us a value on the extreme edges of the distribution of the sample means. So now let's deal with our sampling distributions. Let's say that we have our normal distribution, we'll look at here first. Let's say we have something that's normally distributed with mean 28 and standard deviation of 7. Let's say somebody is at the 90th percentile. Find the 90th percentile. All this is saying is on our curve, we want to find the value here to where the probability of 0.9 to the left. Probability is 0.9 to the left. So we're finding this value. So this would be using our calculator here. We're doing second distribution, inverse normal, 0.9. We're putting in our mean of 28 and our standard deviation of 7. It spits out 36.97. So a value of 36.97 is the 90th percentile. Now, if we're not dealing with means, if we're dealing with proportions, so look at sampling distributions here. Let me look at means for just a second longer. This was for individual values up here. I was selecting an individual out of the population. Let's say this is a sampling distribution. So we're going to have a sample size of n. Sample size of n equals 40. So let's say that we know the population, standard deviation, sigma is 7. And so what this is telling us is, and let's say the population mean, mu, I don't want to get into that. Whatever our population mean is, we are expecting that the mean of these sample means is going to equal it. But I'll talk about that in just a second. So let's say we take all samples of size n equals 30, or n equals 40, I should say. And we're looking at their means. Again, their means are going to form a bell curve if I distribute them. And that's what we're talking about. The sampling distribution is the distribution of all those sample means put on a bell curve. The center of this would be the mean of the population. That is, remember, what we call the mean of the sample means is equal to the mean of the population, the individual values of the population. What I want to talk about is called standard error. Or this textbook actually refers it to as the standard deviation of the sample means. And that standard deviation of the sample means, which is sigma x bar, is equal to the population standard deviation divided by the square root of the sample size. So for this, it's going to be 7 divided by the square root of 40. So 1.107, I'm going to call that, is what would be the standard deviation of those sample means. That's what would govern this curve here, the distribution of the sample means. So what if this were a sample proportion? So what if we get a sample proportion let's just do this. Let's do it the easy way. A sample of 60 items gives 42 with whatever that desired characteristic is. So P for our sample is going to be 42 out of 60, or 0.7. The standard deviation of those sample proportions is going to be the square root of P times 1 minus P over N. So that's going to be the square root of P is 0.7. 1 minus P, 1 times 1 minus 0.7 is going to be 0.3 over N, which is 60. So square root of 0.7 times 0.3 divided by 60. Notice I can put that all in one line like that. 0.0592. That is my standard deviation of the sample distribution of the sample proportion. So the standard deviation of the sample proportions is what that would be. Okay, let's actually get into some of our tests. Now, let's talk about intervals first here. We have 3 types of confidence intervals we're going to find. 2 of them are for the sample mean. We have Z interval and T interval. A Z interval, we know the population standard deviation. For a T interval, we don't know the population standard deviation. So we end up using the sample standard deviation, and then of course we have to use the T interval, so the Z. Now within each of them, we can do a stat interval or a data interval, and these are just functions within the calculator. Stat means we're given, for either one, we're given the sample mean and sample size. So we're given X bar and N. Data, we're given just a list of numbers. So then we have to enter those into our stat, edit, and put it into our list. L1, we put all those numbers in there. So let's take a look, and then of course our third type of interval is for proportion. For proportion, it's always going to be a Z interval. And for proportion, we always have to have N, the sample size, and X, which is the number of items that have the desired characteristic. So let's take a look at sample means first. So for a population with standard deviation of 8, find the 90% confidence interval for the population mean determined by this sample. I'm going to write them off to the side here so I got room to pull up my calculator and still punch these in. So I'm just going to give you these numbers. 31, 42, 53, 37, 58, 44, 49, that's that 1, 2, 3, 4, 5, 6, 7, 41, 38, 51, 45, 46, 37, 45, 52, and 48. So there's my numbers. So what I have to do here first is I have to enter that data. So here they did not give me the sample mean or the sample size even. I can get the sample size by just counting how many numbers are there. They didn't give me though the sample mean, they just gave me the list of numbers. Now I could take that list of numbers and I could calculate the mean and I could punch it in, but it's easier just to hit stat, edit. I'm going to clear out list 1 and I'm just going to enter those numbers. So 31, 42, 53, 37, 58, 44, 49, 41, 38, 51, 45, 46, 37, 45, 52, and 48. Hopefully I got them all entered in there without any errors. So you can see I'm at L17, which means there were 16 numbers in that list. So I'm going to exit out of there. We'll go back to stat, tests. Now I'm going to make my confidence interval. It's 90%, but I know the population standard deviation. I was given the population standard deviation. So this is a z-test, or z-interval at 90%. So I'm going to go down to number 7, z-interval. And I am dealing with data this time. I've got the lists. My population standard deviation that's given is 8. I am in list 1, so I've got to do second 1 to make that L1. Frequency is 1. Your frequency you're always going to want to leave as 1. What that's saying is if you got numbers that are repeated a lot, you can enter them in once and have do the repetition there. Sea level is going to be 0.9 because 90%. And we'll calculate. And there's our interval right there, 41.523 to 48.102. So there is my 90% confidence interval. Now, if I did a 95% confidence interval, do you think it would be narrower or wider? Well, 95%, if I'm looking at that curve, 90% takes a swath this way. 95% would be wider. Let's double check that. Oops, let's do stat tests. 7. All we're going to do is change this to 95%. That's not what I wanted. Hopefully I hit the right keys here. Number 7. There we go. So you can see it is wider. 40.898 to 48.732. It's about 0.65 wider on each side. Okay, so that is a confidence interval for population mean when we know the sample standard deviation, or we know the population standard deviation, and I'm given a list of numbers, so I use data instead of stat. So now let's find the 95% confidence interval for the population mean given a sample of 45 items gives a mean of 32 and standard deviation of 6. So now here, I'm given a standard deviation, but that's not for the population. That's from the sample. So that means this is going to be a t interval. We have a sample standard deviation. So, and I'm not given a list. I'm given the sample mean and standard deviation and sample size. So I'm going to go to stats. This time I'm going to test. This time it's going to be a t interval, number 8. And instead of data, I'm going to use stats. Because I don't have the list of items, I just have the summary information. The sample mean is 32. Sample standard deviation is given as 6. Sample size is 45. Confidence level is 95%, so 0.95 is good there. Hit equals, enter, 30.197 to 33.803. So there is our 95% confidence interval. So it's a little bit quicker if we're just given the summary statistics instead of having to enter all the data into the list. And then our third type of confidence interval, find the, we'll go 98% confidence interval for the population proportion given a sample of 45 items includes 30 with whatever that desired characteristic is. 30 successes, we'll call it for now. So whenever we're dealing with a confidence interval for a population proportion, it is always a z interval. And the calculator has a separate command for that. Clear. So we're going to stat, tests. We've got our tests are listed first. The hypothesis testing listed first. We got to get down to the confidence interval part of the menu here. Z interval, T interval, 2 sample Z interval, 2 sample T interval, 1 prop Z interval. That is the command we want for a prop proportion. This is a 1 proportion Z interval. X, that's the number of successes. That was 30. N is the size of the sample. That's 45. 0.98 is our confidence level. And we're going to calculate. So 0.50319 to 0.83015. You might think that's quite a wide range from 50% up to 83%, but for a proportion, a sample of only 45 is kind of a small sample. Normally you take a larger sample than that for a proportion. So that is all of our confidence interval stuff. If I wanted to know the margin of error for any of these, let's go back here and find the margin of error. The margin of error, I would just take those and I would subtract 48.102 minus 41.523 and divide it by 2. So 48.102 minus 41.523. Now, I didn't put parentheses around them, so I'm going to have to hit equals first, then divide by 2. If I just hit divided by 2, order of operations takes over and is going to mess it all up. So 3.2895 would be my margin of error for that. I can do the same thing here. Subtract those. I'm just going to punch it in the calculator. So 33.803 minus 30.197. Again, I got hit equals, then divide by 2. 1.803. For proportion, same thing. Subtract those. 0.83015 minus 0.50319 equals divide by 2. 0.16348 is my margin of error. So that is my confidence intervals. Now, I can also use those confidence intervals to do a required sample size. And the way this works is we're doing off that margin of error formula. The margin of error formula goes off of a z-critical if it's a z-test. Now, we only can do a required sample size for z intervals because we have to know the population standard deviation. So z-critical times the population standard deviation divided by the square root of n. Well, if I want this margin of error to be below a certain size, I can control that with the size of n. So if I do the algebra to solve this for n, so I have to multiply by n, divide by the margin of error, and then square everything. And that required sample size is z-critical squared times population standard deviation squared over the margin of error squared. Or I could look at it as being z-critical times the standard deviation divided by the margin of error and then all that squared. So let's say for a population with standard deviation of 12, find the required sample size for the margin of error in a 95% confidence interval to be no more than 2. So what we have here is we have sigma of 12, our desired margin of error of 2. Now it might also say what would be the required sample size to be 95% confident that the point estimate will be within 2 of the population mean. That's another way of wording this. So I'm going to go through that again. What is the sample size required, or required sample size, to be 95% confident that the point estimate of the mean is within 2 of the population mean? So the point estimate of the mean is the mean from that sample we take. And of course, we'll use that first for our confidence interval. So anyway, now we need to find a z-critical. This is 95%. Remember, 95% confidence interval is the 95% out of the middle. So that means there's 2.5% on each side. So what we look up to find that is we're just going to look up 0.025 on the calculator. So inverse normal. So second distribution, inverse normal 0.025 should give us negative 1.96, and there it is. 1.96 is what we'll use. So we'll use a z-critical 1.96. So our required sample size, n, I'm going to use the second version here, 1.96 times 2 divided by 12, and then all that squared. So parentheses, 1.96 times 2 divided by 12, x squared. I get something way off there. Oops, I got that backwards, that's why. I put in My standard deviation on bottom. The standard deviation has to go on top. 12, and my margin of error on bottom. 2. That'll work a little bit better. So let's try that again. 1.96 is my z-critical times my standard deviation of 12 divided by my desired margin of error of 2, then squared. That's much better. 138.29. 138.3. When we get this sample size, remember that is the minimum sample size to be within it. Now if we rounded that down, we would be below the minimum. Even though it's 138.3, we have to round it up to 139. Always round up on the sample size, because if we round it down, we're going to be below our minimum size, and it's not going to stay within that desired margin of error. Now, what if it were a sample proportion or population proportion? Find the sample size required to be 90% confident that the sample proportion is within 0.03 of the population proportion. Now, there are two cases here, and I'm going to do them both. One is if we have an estimate of the population proportion. The other is if we have no estimate. So let's say we are told that we think the population proportion is about 0.2. So then our sample size, n, is going to equal p times 1 minus p over our margin of error squared. So to deal with that, we're going to punch in this estimate of the population proportion. So it's going to be 0.2 times 1 minus 0.2 over, we want to be within 0.03 squared. So I'm going to do 0.2 times 1 minus 0.2 is just 0.8, so I'm just going to type that in. Divided by 0.03 squared. 177.77. Now again, that's the minimum, so we have to round it up. So we're going to need n equals 178. If we don't have an estimate, then we're going to have to use 0.5. So now n is going to be 0.5 times 1 minus 0.5 over 0.03 squared. So if we punch this into the calculator, 0.5 times 1 minus 0.5 is also 0.5 times 0.03 squared. Now notice there's no parentheses around it because it's just the 0.03, just the margin of error that's squared here. Equals oops, helps if I get that in there right. I've got to change that to divide, not times. A lot of little missteps today. Sorry about that. So there we go. 0.5 times 0.5 divided by 0.03 squared. 277.77 again. So it's 278 that rounds off. Now notice, that's significantly higher. This is only 177.77. This was 277.77. These are larger sample size. The reason for that is because I had to use the 0.5. If I use 0.5 as my estimate for P, that gives me the largest possible sample size. Anything bigger or smaller than 0.5 will give you a smaller size. So here we had an estimate of the population proportion. We used that so that we could limit to get a smaller required sample. But if we don't have that, we can always use 0.5, and that'll give us a sample that's large enough to guarantee. It may be way smaller than that for the margin of error, but it'll guarantee that we have a large enough sample to get within that margin of error. Okay, so what I'm going to do, that it ends the part on confidence interval. So I'm going to end the recording here, and we will come back and do hypothesis testing separate.